All right, so for significant zeros, these rules apply to numbers that you were given. Okay, they're written down somewhere. It's not numbers that you necessarily have recorded in the lab because you should have handled significant zeros correctly anyway. But if you think about what you do when you do measurements, there are certain zeros that just logically oh yeah, that makes sense. That's reasonable. Okay, if I'm measuring the mass of something and I get 25.00 grams of whatever the material is. Let's say since we did a recent lab where we measured table salt. This is table salt. So but if you think about it, that those two zeros, well, those are significant. That's telling you something about the precision of the measurement, right? Because the measuring instrument measures to the hundredth of a gram. Well, that zero is important because it tells you it measures to the hundredth of a gram. If I only write down 2.5 and don't write the 0.00, well, you can't tell how precise the measuring instrument was. Okay, and precision is important in what we do in the sciences and engineering and business and industry and such. It's all important. So those two zeros are significant, and so the rule that applies to that is that there's an informal rule that I often use. I say trailing zeros are always significant. Okay, if there's a decimal place, trailing zeros are always significant if there's a decimal place. Okay, so there's a decimal place here in the number, so those trailing zeros are significant. And it doesn't matter whether they're after the decimal or before the decimal. If there's a decimal, trailing zeros are significant. Okay, so if I have, let's say 20.00 grams of NaCl, well, that trailing zero is significant because I've got a decimal place. All three zeros are trailing zeros. They're all significant because it's a decimal place. On the other hand, if I have this much sodium chloride, there's no decimal place. So I really don't know if the trailing zeros are significant or not, and so we treat those zeros as if they are not significant. That makes sense? Yes? All right. All right. Now if I have 205.0 grams of NaCl, then this zero that's in between two significant digits is also significant. Okay? Got that? All right. And that makes sense. I mean, if you leave out that zero as if it's not significant, well, that wouldn't be 205 anymore. It'd be 25 or something. That's not anywhere close to the same number. So that zero is also significant. That zero is significant because it's a trailing zero when there's a decimal place. Okay? Now let's say we have a leading zero. So let's say we have 0.025 grams of NaCl. Okay, now this would be measured on a balance that's more precise than the ones we have in this class. Those are called analytical balances, but those leading zeros are not significant. Okay, leading zeros are not significant. Okay, so the number of significant digits in this number is 2. The number of digits that are significant in this number is 4. All 4 are significant. This number here is going to be treated as if it has only one significant digit because these trailing zeros aren't significant. There's no decimal place to tell us they're significant. Okay, there's 4 significant digits here and 4 significant digits here. Okay, that makes sense? Now there's a little trick that chemists often use, and you may see it in other sciences as well, but let's say we have 200 here. Okay, in order to show those two zeros as significant, I need a decimal place, right? So if I just put a decimal place there, that's a little trick we use sometimes in chemistry. It doesn't happen very often, but occasionally it does. If you have a zero in the ones place that you need to show as significant, you can put a decimal place there with no trailing zeros after the decimal to show that those two zeros are significant. If this one's significant, then this is between two significant digits, and this is also significant. Okay? Any questions about that? So, let's say we have this number here. So this is 21,053 milliliters of salt solution. How many significant digits in that number? 5. because the 0 here is between two significant digits, so it has to be significant. Okay? All right, so we've got this number then, this measurement. How many significant digits are there? 5 again. All three of these zeros are significant because they're trailing zeros when there's a decimal place present. That makes sense? And the non-zero digits are always significant. Okay? Okay, so how many significant digits here? Nope. 3. Leading zeros are not significant, so these 3 zeros are not significant. The trailing zero in the presence of a decimal place, that trailing zero is significant. The non-zero digits are significant. That makes 3 significant digits. Okay? So let's say that we have a number like this, where we have 21,000 milliliters of salt solution, and I need to show that this one digit right here is not significant, but these other 2 zeros are significant. I've done this measurement. This is what I have, or I've done the calculation. I need to show that I have 4 significant digits and the 0 is not significant. Okay? The way that you handle that is with scientific notation. Okay? So here's the rule about scientific notation. If you have to round off a number in the ones place, you must write your answer in scientific notation. Okay? It's not required in any other case. You can write a number that has, 100 zeros between the decimal and the first non-zero digit if you want to. Okay, I'd prefer you write a number like that in scientific notation, but it's not required unless you're rounding off a digit in the ones place. May also be rounding off a digit in the tens place or the hundreds place, but if you're rounding off a digit in the ones place, your answer must be written in scientific notation. Does that make sense? So if we're rounding off this 0 right here, okay, then I have to write the answer in scientific notation. It's not enough to write a decimal number. You have to write it in scientific notation. And scientific notation has the decimal between the first and second non-zero digit. Always. Scientific notation has the decimal between the first and second non-zero digit. Okay? So if I want to do that, I'm going to move the decimal place like this. 1, 2, 3, 4 places to the left. I want to draw an arrow to show that I'm rounding off. And I'll write my answer as 2.1. I want to show these 2 zeros as being significant, so I'm going to include those, times 10. And since I moved the decimal place 1, 2, 3, 4 places to the left, it's times 10 to the 4th milliliters of salt solution. Okay? Does that make sense? Now, if I want to move my decimal place to the right, then I'll have a negative exponent. Let me show you what I mean by that. 0.00210 milliliters of salt solution. Okay? And it's not required that I write this in scientific notation. Is everybody clear with that? Not required. But if I want to, for convenience, I want to make it an easier number to read, and that's the case a lot of times when you have a bunch of zeros. In this case, you've only got 2. But let's say we had 8 zeros in there. It's easier to understand what the number is if you write it in scientific notation. Not required, but easier. So I'm going to move my decimal place 1, 2, 3 places like this. And then, actually, this is not going to be a rounded off number. This is actually equal. Okay? It's only rounding off when you're getting rid of a digit. So it's equal to 2.10, and since I moved the decimal place 3 places to the right, it's times 10 to the negative 3 milliliters of salt solution. Okay? Everybody clear with that? And notice in all these numbers, I've included units of measurement and chemical species. Okay? it is very important that anytime you're recording a number that applies to a unit of measurement and or a species, that you include those, that you tell me what the number is. So I want you to think about just numbers by themselves without any identifying information as being theoretical. Okay? They're not real numbers until you tell me what it applies to. Okay? And here's the example I often use. How many of you want to make 100? Okay, how many of you want 100? Okay, I see a few hands, all right? Some of you are you're scared because you know something's coming up, right? 100 kicks upside the head. Yeah, right. You thought I was saying one thing and I didn't specify, did I? Right? So if I don't specify what the 100 applies to, you're answering a question. It's like signing a contract when you haven't read it. Okay, you don't know what you're signing for. You don't know what you're saying okay to. All right? Unless I tell you what it applies to. All right? That makes sense? So make sure in the sciences, you've got to be clear. Make sure that when you write a number or measurement down that you're telling the person who's reading it, and usually that's me, what it is that applies to. If you don't include units of measurement when they apply, if you don't include species when it applies, I count off points. Okay? If I ask you to round this number to 4 significant digits and you just put 2.10 times 10 to the 4th and you don't include milliliters of salt solution, you lose 2 points right off the top because you don't have the units of measurement and you don't have the species. You with me? By the way, that's kind of the shorthand we use in chemistry for solution. Okay? Just a way of writing it in short, fewer letters. Save us some time. All right? And milliliters, we write milliliters like this with a small m and a capital L because it's hard to tell the difference between a small letter L and the number 1, or for that matter, a capital I. Okay? So whenever you're writing liters, please write a capital L for that. If it's milliliters, it's M capital L. If it's just liters, it's just capital L. If it's deciliters, it's D, small letter D, capital L. Okay? Got it? So it just makes it clearer for that. Okay? There's a lot of things we do that. Why do we have to do it that way? Because it's clearer when you do. Okay? Especially when you're writing things down by hand. And writing by hand, computers are becoming so ubiquitous and stuff, and people don't like to write stuff. But you know what? There's a lot of things we do in chemistry where the computer's it's just faster to write it by hand. When we do stoichiometry or dimensional analysis, it's faster to do it by hand than it is on a computer. Okay? Just because you have to do so many keystrokes and so many little this and that's that after a while it's just easier to do it by hand. Okay? And so we're going to be, and besides, doing it by hand, writing things down is a kinetic learning activity. When you're moving your hand to write something down, you get more input into your brain than if you're just typing it out. Okay? Just because you have to move your hands to make it happen. All right? So it's a good way to learn when you take notes. Okay? And I know we kind of get, as a society, we're kind of getting away from that, taking notes on the computer and such, but it really does help you to take notes by hand. It helps you to remember things, okay, when that's possible. And some people don't like to do that, and that's fine, but it does help. Okay, when we're talking about dimensional analysis, think about dimensions in a little bit different way. We often talk about dimensions like being length and width and height, right? Okay, and they are dimensions, okay? But in this sense, dimensions mean just any kind of measurement, any class of measurement. So if I'm measuring length, I can measure length in meters or millimeters, okay? And that length measurement is a dimension, okay? That makes sense? So the unit of measurement I'm using for that is the dimension we're talking about, okay? So we're analyzing dimensions of measurement. If we're talking about volume then, well, that's actually 3 dimensions, okay, because you've got a length, width, and height that makes up that dimension. We might call it milliliters, but it actually is taking into account 3 different dimensions, length, width, and height. So what we're doing then is really analyzing, by the way we're handling it, the units of measurement, and in this case also the species. Okay, the dimensional analysis really more refers to the units of measurement, than it does the species, but we include that in there because it makes more sense to do it that way. Just it kind of eases things out, makes it easier to do. Let's say we have a problem like this. Suppose we say that okay, so here's a dimensional analysis type of problem. Later in the semester, you're going to find that there are equalities that you are just going to have to figure out. You have to calculate them. But right now, we're beginning this process, I'm telling you up front what two things are equal. If you just analyze what the problem is stating, okay? If we read this problem, we see that as long as the temperature is 0 degrees C and the pressure is 1 atmosphere, that's what STP is, standard temperature and pressure. Standard temperature is 0 degrees C, standard pressure is 1 atmosphere, okay? As long as we have standard temperature and pressure, there's this many grams of hydrogen gas and a liter of hydrogen gas, okay? So what we have here is actually two things that are equal at STP. All right, we have 8.99 times 10 to the negative 2 grams of hydrogen gas. Now, hydrogen gas is a diatomic molecule, so that's why I wrote it as H2. All right, the symbol for hydrogen is the capital H, but there's like 1, 2, 3, 4, 5 diatomic gases on the periodic table. Hydrogen is one of those. So anytime you write hydrogen, normal hydrogen, that's not combined with anything else, it's just by itself, like you're using hydrogen as a fuel to burn or something like that, then it's going to be H2. And that means that this many grams of hydrogen gas is equal to 1 liter of hydrogen gas at STP. Okay? The question here doesn't say that this hydrogen gas is at STP, but you kind of assume it because the two sentences are right there next to each other. We haven't changed anything. It doesn't say about changing anything. So we're going to make the assumption that this many grams of hydrogen gas is also going to be at STP. Now, we just learned about scientific notation, okay, or reminded you about scientific notation. So we could also write this number as 0.0899 grams of H2 equals 1 liter of H2. Okay? I don't know why I've got a, I guess I just bumped the table there with my felt marker, and it looks like I've got a decimal place there. Okay? So if I were to move the decimal place 2 places to the right, 1, 2, I'd have 8.99 times 10 to the negative 2. Okay, so that's the same number as that. Okay? Either one of these is fine. You can use either way of writing it. Okay? So what I want to do is to take whatever the starting amount is and put it over 1. This is not a starting amount. Okay? This is telling you that this amount is equal to this. This is where you get the equality statement from to build a conversion unit. The starting amount is the amount that stands alone, you might say. Okay, that's just one way to think about it. All right, and so we're going to take that 2.55 grams of H2, and for most of the stoichiometry and most of the dimensional analysis we do in here, you can always put your starting amount over 1. Later in the semester, there'll be some things where we kind of tweak some of that. We can do some other things too. But for right now, this is the place to start. We're going to put it over 1. It can't hurt to put it over 1, but there are times when you actually have one kind of starting amount you can put on the bottom. It makes it easier to solve the problem. We'll get to that. For right now, we're just putting it over 1. And then from this equality statement here, and I'm going to use this one on the bottom. There's two equality statements. They're the same thing, but I'm going to use the one on the bottom. What I want to do is look at the equality statement and find which side of this equality statement has the same units and species as I have on the top of this fraction. Okay? And it's this side over here. So that's the side of the equality statement I'm going to put on the bottom of this conversion unit. The conversion unit for us is always going to be a fraction. You're going to always build conversion units. Every time you have to have a conversion unit in this class, you also have to have an equality statement. If you don't write the equality statement, that's 5 points you lose right there. Okay? 1, 2, 3, 4, 5, 6, actually 7 points. I'm sorry, I said 5. It's 7 points you lose if you don't have the equality statement. Okay? I want you to know where conversion units come from, because that knowledge is going to help you in the future to be able to make conversions even better. Okay? I had another teacher stop in yesterday asking me about conversions, okay, because she's teaching a new class. She's having to do conversions. She hasn't done conversions like that in years. And, you know, for me, it's like I can do this in my sleep because I do it all the time. But she doesn't think about it the same way I do because she doesn't use it. I want you to use it so that when you take that kind of class in the future, for you, it's going to be like super easy. You won't even have to write down equality statements anymore because you'll know when you see it what it means, okay? And that's the idea. If you don't use it a lot, you won't have it imprinted in your memory to be able to in a usable form. And I want you to have that because it really is used ubiquitously everywhere all the time, but people don't know what conversion units are. They just plug in numbers not really knowing what they're doing. I want you to know why it works, okay, because it's so important in chemistry. It really is. All right, so I'm going to take this side of the equality statement and put on the bottom 0.0899 grams of H2, and the other side of the equality statement, this one goes on the top. Now, the tricky thing is when I have 1 liter of H2, you need to know that that 1 is treated as if it's infinitely significant. It is, okay? When you have just a 1 with no decimal, it's just a counting number. And counting numbers are infinitely significant. That means I could put as many zeros after a decimal as I wanted to, and it would still be what that number is. It's just like you. There's one of you. Okay, I can't have 1.5 of you. Okay, I can't have 0.8 of you. It's you, right? So there's one of you. If I put 1,000 zeros after you, it doesn't change the fact there's one of you. Okay, it's infinitely significant. All right, so we're going to not even consider this when doing significant digits in this number. All right, now let's do the math first. All right, so we're going to take 2.55 and we're going to divide it by 0.0899. And I hope you have a standalone calculator, okay? You're not going to be allowed to use your cell phone calculator on tests in here, okay? Because you can communicate with those and ask somebody, how do I do this? You know, by text or something. You have to have a standalone calculator that doesn't communicate, no wireless, communications with your standalone calculator. So make sure you've got a scientific calculator that you can use for tests, all right? So we've got this number, did I divide? For some reason I didn't divide. Where's the divide button? Okay, let's put in second enter and do divide. Somehow I managed to leave that out. And then hit enter and I get this number here. So I got 28.36484983. That's the number I have left. That's just the, now your calculator may have a few less digits or a few more digits. That's okay. Not a problem. You're going to end up rounding off numbers anyway, but I want you to write down all the digits that your calculator shows. Okay? If your calculator is set up right now so it's automatically rounding, take it off of that. Okay? You don't want it automatically rounding for you. You want to do your own rounding. Okay? So if you need help with that, come and see me. I'll try to help you. But there's 3 significant digits here. And how many significant digits here? 3, good, because leading zeros are not significant, good. And that means that we want our final answer to have 3 significant digits. What you want is of the measured and calculated numbers, these two numbers, this is measured and this is calculated. Okay, of the measured and calculated numbers, you want to have your final answer have the same number of digits as the one with the least digits. The least digits among the measured and calculated numbers. This is a counting number, this is a counting number. You're not going to consider those, okay? This is really more a placekeeper than a counting number, but it's still a counting number. So we want 3 significant digits in our final answer, and that's 1, 2, 3, and these digits all get rounded off. Now what I haven't included here yet is the units of measurement because I haven't analyzed the dimensions yet. So I've got a dimension of mass here and here, and that's measured in grams, and so we're going to cancel them out. Okay, just like x's and y's in algebra. And we can also cancel out h2 here and here. Okay, we include that in our dimensional analysis, and so we have only units of liters and h2 left, liters of h2. Okay, and that's the dimensional analysis part. Now we're ready to write our final answer. We draw an arrow. Arrows are the only operator. It's like an equal sign or a times sign or a plus sign. It's an operator in math. You have to show an arrow to show that you're rounding off. It's the only operator allowed to show rounding off. You can't write, you know, an equal sign or a squiggly equal sign. You have to use an arrow to show that what you're doing is rounding off. And so we're going to round it off to these 3 digits. This 6 here, the way that we round off in high school chemistry, because this is a number that's 5 or greater, it's going to make this number round up. And so we're going to take 28.4 liters of H2 as our final answer. Now the way that I described rounding off here, I described it in that way because there actually is a better way to round off. We don't do it in high school because you've been used to doing this 5 and greater rounds up, right? Thing since what? Elementary school? What grade? 3rd grade maybe? I don't know how early it started. We're not going to try and give you the new way to do it. But just as a heads up, when you get into a college science class, there's going to be some professor that may ask you to round in a completely different way. And it's a better way. This actually propagates errors when we do it this way more than the other way. The other way is less likely to propagate errors. So there are a lot of professors that prefer you to do that. All right? So that's dimensional analysis. Do you want more practice problems, or are we good with all that?
I'm pretty good.
Anybody else? Okay. All right. So there are different rules for addition and subtraction as compared to or contrasted with the rules for multiplication and division. And we used the multiplication division rules for rounding here. Okay, the addition subtraction rules are a little bit different. There's a 3rd rule which we won't learn in here, but I'll remind you about it when we get to asses and bases. When you're doing exponents and logarithms, there's a rounding rule that we don't use in here, but again, it's like one of those things you might find in college. They're going to expect you to know the rounding rules for logarithms and exponents, but we don't worry about it so much in high school. Okay, so we're going to learn 2 different rounding rules. So for addition and subtraction, the basic rule that I use is you line your numbers up vertically. You don't add horizontally, you always add vertically. And any numbers resulting from an empty slot to the right get rounded off. It's just kind of a simple way to explain it, okay? That's probably a more formal way of explaining it, but that's the way that I like to teach it, okay? So let's add these numbers. So we were using table salt. Let's say we were in our lab recently. So let's say I have 1.5 grams of sodium chloride, which is table salt. And we're going to add that to 25 grams of table salt, and add that also to 0.497 grams of table salt. Okay? And subtraction works exactly the same way. You just put your numbers vertically. Now remember, when we have numbers after the numbers to the right compared to where the decimal is, tell us about the precision of the measuring. Okay, the instrument that measured this measuring instrument must have only measured to the 1/10 of a gram. This measuring instrument only measured to the gram, and this one measured to the 1,000th of a gram. Okay, and so what we want is a number at the end when we add them together that represents the least of the more precise measurements. The least precise measurement. It's kind of the same thing as this. We had the number with the least digits, the least precise measurement. That makes sense? It works out kind of the same. There's actually a lot more to it than that, but we're not going to get into the deep details. Basically, you just need to know how to get it done. Okay? So we're going to take 1.5 grams of NaCl. Okay, and notice I left a little space here because I know I have more digits to deal with over here. Just, I know to do that. You might think about that in the future. And 25 grams of NaCl. And then we've got 0.497 grams of NaCl. We're going to add all these together. Okay. Now you can't put extra zeros on there, and I know you've been doing that since maybe third grade or second grade or something. You've been putting, if you were adding these up in any other class at any other time, you would have put a .000 here, right? You can't do that because in physical sciences, like chemistry and like physics, when you put extra zeros on there, you're telling somebody that's the precision of the number, and it's not. So I don't want you putting those extra zeros on there because that would be lying. In a chemistry class, put extra zeros in there, you're saying the instrument measured to that precision, and it didn't. Okay? So what you're allowed to do, if you want to, and it's not required, is you can put arrows here to show where there would be those empty slots or where zeros you might have put in previous classes or some other class. Okay? So the arrows can help you keep it lined up. That's what I like to do because it helps me to keep it lined up. And my writing is not the greatest in the world, and so in order to make sure that I have things lined up nice and neat, I'll use arrows. So I can do it in the calculator. 1.5 plus 25 plus 0.497. And you may be able to do this better in your head. That's fine. You can do it in your head. You don't need a calculator really for this one. Now this isn't canceling any digits. Okay, we're not multiplying digits, so we don't need to have a, do anything with the units of measurement. Adding doesn't change the units of measurement of the species. But because I have empty slots in this column, and this column, and this column, these three digits are insignificant. The reason they're insignificant is we don't know what those digits should have been. Okay, what if we had measured this amount of sodium chloride on this device here? Where we'd have one more digit here. It might be a 0, it might be a 9, so we don't really know what that number is. That's why we're rounding it off. Okay? And so we're going to round it off just to 2 significant digits. And because we have a 9 in the first position that we're rounding off, it rounds this 6 here up to a 7. So we're going to have 27 grams of NaCl. And that's our final answer for this problem. Okay? And it works the same way for subtraction. Okay, when you subtract, you use the same rules. Line up your digits, get rid of any digits or round off any digits at the end that result in empty slots to the right. Okay, I didn't round off any digits to the left due to empty slots. It's only digits to the right we're rounding off. You got that? Okay. I've had students get confused about that, so I try to make sure that I'm as clear as possible on that subject now. So we're going to subtract 14.06